Okay, so what we want to look at now is we want to look at vector spaces. Right, so what's a vector space? A vector space is a set, right? So a set containing, well, usually something that's basically vectors, right? And then with that set, you're going to have two operations, which are vector addition and scalar multiplication, right? Okay, so probably a basic example of a vector space is R2, right? So R2, how I have it written over here is that this XY you don't want to read as, say, a point, right? What you want to do is you want to read this as a vector, right? What we're doing is we're considering all vectors over here, right? So the x and the small x and the small y can be anything, right? So by this you mean that all possible vectors in the plane, right? And how you add the two vectors, you just add the components, right? So this is your set over here, and one operation is vector addition, and the vector addition is you for two vectors. In order to add them, you just add corresponding components. And the scalar multiplication for a vector space, right? In this, well, for this particular vector space, is you have your vector xy, and you multiply by a scalar c, right? And this scalar multiplication, how it's actually done over here, it's going to be c times the first component, so you get cx, and then c times the second component, so that you get cy, right? Okay, so this particular case of vectors in the plane with vector addition and scalar with the operations of vector addition and scalar multiplication, you can actually see this geometrically, right? So let's look at this example here. Okay, so what you have is, this is, the notation is slightly different, but this 6 minus 9, this is a vector in the plane, right, in R2. This is also a vector in the plane, right? And what they're doing here is they're showing that if you take, in order to add the two vectors, right, and this is how you do it in the standard sort of way, you have your vector u and your vector v, and when you add them, what you get is you get the sum of vectors, and you get that by, for example, you take the tail of this vector, drag it onto the head over here, right? And then the resultant sum is given by that dashed line over here, right? This is the sum, right? Okay, and I'm sure you would have seen this before, right? So this is an example of vector addition. Okay. Right, okay, and now let's look at the scalar multiplication. What does the scalar multiplication mean, right? Okay, so here I have a vector to start off with, which is 3, 2, right? And what this graphic is going to do is, this graphic, it is going to take this vector and multiply it by a scalar, right? So your vector over here, and you're doing a scalar multiplication. It starts off at 1, right? But what the graphic does is that, what the video does is, you can adjust the scalar, right? Okay, so you see that if the scalar is now 1.5, right, you're going to get 1.5 the scalar times this vector, and it's 1.5 times the 3, right, which is 4.5, right, and then 1.5 times 2, which would give you 3, right? Okay, so how you actually work it out is, you're going to take, to do the scalar multiplication, you take the 1.5 and you multiply it against each of the components, right? And notice what it does for you, right? What it does is that it makes the vector, well, because the scalar value is bigger than 1, it will actually increase the length of the vector, right? Okay, so that is the two operations of vector addition and scalar multiplication, right? Okay, so a set V of vectors with an addition and a scalar multiplication is a vector space, right? provided these 10 properties hold, right? Okay, so first of all, these properties here, right? Well, it's 10, but you could break it up into groups of 5, right? So the first 5 has to do with the vector addition, right? If you notice up to here, right, everything is just involving addition. This is involving addition. This is involving addition, right? So the first 5 have to do with the vector addition. And then the next 5 involve the scalar multiplication, right? And sometimes well, with these over here, what it involves is the scalar multiplication together with the vector addition, right? Okay, right. Right. So I mean, it's a lot of axioms over here, but well, what's really the point, right? The point here is that the point is, okay, if you have a set, right, and you have some operation, addition and scalar multiplication defined on it, right, and if it satisfies these 10 properties, then you know it's going to be a vector space, right? Okay, so for example, this one over here, right, this is your set, right? And these are the two operations, vector addition and scalar multiplication. You can show that the set given your vector addition and your scalar multiplication, it will satisfy these conditions. So this would actually define a vector space for you, right? On the other hand, if you consider, say, this set over here, so this is polynomials of degree at most 1, right? So an example for polynomial of degree at most 1 is this, right? 3 plus t, right? So you have no t squared or anything like that because the degree is at most 1, right? Okay, so the set of these would look like 3 plus t, 2 plus 6t, and so on, right? And given this set, right, what you can do is you can define something that would work as a vector addition, and what we use in this case is for this set of polynomials is just standard polynomial addition, right? So you want to remember that if you're going to add two polynomials, what you do is you add the constant terms, so the 2 plus 1 is 3. And then you add the terms in the power of t, right? So 3 plus minus 2t gives you 3 plus t, right? So this over here is what you'd use as vector addition, and then the scalar multiplication comes from how you multiply a scalar times a polynomial, right? So 2 times this polynomial is 2 times 1 plus 2 times 3. So you get 2 plus 6t over there, right? Now this over here, you can in fact show that this is a vector space, and we would do it. It's done in the notes later on. It's done over here in a more general setting. Okay, so this over here is for any degree n polynomial, right? Once here. Okay, so the Pn over here is you're considering polynomials of degree at most n, right? So you must have some kind of cutoff. Well, for these examples, we want a cutoff point, right? Anyway, so this P1 over here, this set with your vector addition and your scalar multiplication, it will actually also satisfy these 10 conditions here, right? Okay, so, well, why do you really care, right? Well, why you care is you can show that this is a vector space, and we can show that this is a vector space, right? And once you know it's a vector space, then it's going to have certain properties, right? And the properties of the vector spaces, such as like subspace, dimension, and so on, right? It doesn't really have anything to do with the fact that it's polynomials over here, right? It just has to do with these operations, really. The vector addition, right? This one, and the scalar multiplication. Once you have these properties over here and they satisfy these 10 conditions, there's a lot of theory for this, and you can apply the theory to say sort of things about this, right? You can say a lot of things, right? So the point is, you start off with, say, actual, probably like genuine vectors over here, right? Or you could use polynomials, or you could use other objects over here, right? But once you show as a vector space, you can apply like a lot of theory to it, right? and your vector spaces, and so it's like a standard construct that you use in linear algebra, which you will need, which is used in other like applications and so, right. And if you take a look at uh, your web page, that the course web page. Right, you see in the applications and so, right? So it used like the linear algebra and the vector spaces. You use it in controls, use it in signal processing, and so on, right? So yeah, you use it in coding theory and so on, right? Okay, so the point is, whatever, once you have these objects, right? Okay, once you have an object like this, an object consists a set consisting of vectors, and you have vector addition and a scalar multiplication defined on it. Once you can justify that it satisfies these 10 properties, then you can apply a good amount of theory, right? Okay, and likewise over here, right, given this set of objects with your vector addition and a scalar multiplication, you can apply the same theory, right? And matter of fact, this is two-dimensional over here, and this is two-dimensional over here, right? So as far as vector spaces are concerned, matter of fact, these over here will have this R2 over here and these polynomials over here. They will have, they're essentially the same as far as vector spaces are concerned, right? Okay, but we will get to that. Alright, so what I want to do now is I want to explain these axioms here, right, as best as I could, right? Okay, so your most interesting ones actually are the closure, right? Your additive closure over here and the scalar multiplication closure, right? Okay, so let's look at these two first of all, right? Okay, so in order to do that, what I'm going to do is I'm going to consider my vector space, right? So this vector space is going to consist of three-dimensional vectors, but I'm actually going to restrict myself to the xy plane, right? So the picture is this over here, right? Okay, so the black part over here, this is a set of vectors v for this example, right? And this is going to be my vector space here, right? Okay, so the vectors consist of xy. So for example, this black one over here, this black one over here is from here to here is the vector 3, 0, 0, right? They use column vector notation over here, and I use row vector notation over here, but it's, for our purposes, it's the same thing, right? We'll probably fine-tune that later, right? But you just want to read this 3, 0, 0 as just as a row vector, right? Okay, so this vector 3, 0, 0, right, is in the xy plane, and likewise this vector over here 0, 4, 0, right, which is this one over here, right, that vector is also in the xy plane. Notice this line in the xy plane, right? Okay, so what do I mean by additive closure, right? So additive closure, your definition of additive closure is that if I have two vectors in the vector space and I add them, the result must remain in the vector space, right? So it's closed, right? It doesn't jump out of the vector space, right? It remains in the vector space, right? Okay, so right, so the vectors that I'm looking at is the 3, 0, 0. I'm using an example, 3, 0, 0, which is this vector over here, and the 0, 4, 0, which is this vector over here, right? Okay, so I have, this is, if you want, this is my u over here. Matter of fact, it's labeled here. U is equal to 3, 0, 0. The v is equal to 0, 4, 0, right? And well, you see what happens is that when I add them, I get something that again just lies in the xy plane, right? So when I add them, I get this over here. I get this guy over here, right? So I get this vector, this red vector over here, right? So this, when I have two vectors u and v in the vector space and I add them, I get something that also lies in the plane, right? What I don't get is, okay, what I don't get is when I add these two vectors, I'm not going to get something that actually jumps out of the plane, right? So I'm not going to get something like this over here, right? Okay, so this over here, I wouldn't get it being a vector space means that it's not going to jump out of the plane, right? Okay, so this is the vector, this is the u, this is the v over here. This is the actual answer in red, right? There's, if I add the u and the v, right, the fact that it's a vector space means that it can't jump out to the plane, right? It can't jump out like that, right? Okay, so the idea of the closure is that if you add two of them in the xy plane, you're going to get something that remains in the xy plane, right? Because your set of vectors is the xy plane, right? So from you add two vectors from your xy plane, the result will remain in the vector space, right? So that is what the closure is. You don't jump out, right? You will remain, right? So yeah, the answer is the red guy, not the black guy, right? And now let's see if we could understand what the scalar closure is, right? Okay, so the scalar closure is saying that if I have a vector in the vector space and I multiply it by a scalar, then the result also remains in the vector space, right? Okay, so for example, I have this vector 1, 1 over here, right? Okay, so I have a vector 1, 1, 0 here, right? Okay, so this is in the xy plane, right? And I'm going to multiply it by this scalar 3, right? So what do I end up getting, right? So what I end up getting is 330, right? Which is this red vector over here, right? Pink vector over here, right? Okay, so you want to notice that the scalar multiple of this vector stayed in the xy plane, right? It didn't jump out of the xy plane or anything like that. It remained in the xy plane, right? So that's the idea of the scalar closure, right? If you have a vector in your vector space multiplied by a scalar, then it actually just remains in the vector space, right? Which in this case, the vector space that we're talking about is the xy plane. Okay, so we looked at these two axioms to get an understanding what they meant, right? Additive closure and scalar closure. Let's look at the others, right? We'll use this video by James Factor, right, to illustrate the other axioms. Alright, okay, so it's the same axioms that I have, right? Probably might be in a different order, but they're the same 10 axioms, right? Notice that you have 5 vector addition and then you have 5 for scalar multiplication, right? Okay, so, well, what's the first one, right? The first one is he's trying to justify it's closed under vector addition, right? So he's taken these two vectors in the plane. Now what he's working with here, okay, so I need to tell you what vector space he's working with, right? So what vector space he's working with is he's working with vectors, this vector space here, which are vectors in the plane, right? So you want to notice that this here, this is a vector in the plane and this is a vector in the plane, right? Okay, he's not, what I did over here is I looked at the xy plane embedded in three-dimensional space, right? So what I looked at previously was this over here, right? So here, this example that I just used, right, was the xy plane in three-dimensional space, right? What we're gonna look at now is just the xy plane by itself, right? So it's a plan view of this over here, right? So just the black part without the z-axis. You're just looking down from the top, right? So in other words, normal xy plane, right? So that is the vector space we consider in this video, right? We consider it at least the video I'm going to show you now, right? Considering this vector space over here, right? Vectors in the plane. Okay, right, so he has two vectors in the plane, and what he does is he drags them together, right? To illustrate, well, that illustrates the addition, right? But he's also wants to justify that, well, when you have these two vectors here and you add them, what you get in is, okay, notice the 6 plus the 6 is 12, and the minus 9 plus the 7 is minus 2, right? Okay, so when you add these two vectors by adding them component wise, right, you could interpret it graphically by taking the tail of this vector and adding it to the head, right? And then the result is you connect the tail of the first vector to the head of the second vector, right? Okay, but the key for to talk about like closed under vector addition, right? So the additive closure, right? Notice that this vector here is in the plane also, right? All right, and then he's just doing an example of the vector addition, right, with two different vectors here. Okay, so in this case, the u plus v, again, you just add in the components. The 3 plus the 5 is 8, and the minus 4 plus the 4 gives you 0, right? And this vector, again, lies in the plane. Right, okay, so now what you're looking at is associativity, right? Okay, so associative, when you talk about an addition being associative, right, means that you add in three things, right? Okay, so you add in three things over here. Notice you add in u, v, and w, right? Okay, and the associative means that okay, so if you're going to add three things, right? Well, how do you do it, right? Now, normally what you do is you add the first two, and then you add the last one, the third one, right? But you could also add the last two and then add the first one to that, right? You want to make sure that you keep in the order over here, right? Well, okay, this is abelian, so it doesn't make a difference with the order, but still you want to try to maintain the order, right? So you add the first two and then add the third one, or add the last two and then add the first one. You get the same answer in both cases, right? Okay, and you could think of this in terms of, say, like normal addition of say like integers, and so is also associative. So if you want to add 1 plus 2 plus 3 to give you 6, right, you could add 1 plus 2 to give you the 3, and then 3 plus 3 is 6. Or you could add the 2 plus 3 to give you 5, and then add 1 to it, right, and you get the same answer, right? So associativity has to do with adding has to do with when you have an operation with three elements in it, right? One example of something that is not associative is cross product, right? So if you try taking, say, if this was cross product over here, right, then you'd realize it doesn't always hold, right? So not everything is associative. Most things that you probably come across, right, would be associative, but not everything, right? An example of something that is not associative is cross product, right? So you can try cooking up some examples. Probably use I, J, and K, right, and take a cross product, and you realize that cross product is not associative, right? But that's not what we use in here, right? What we use in here is not cross product, right? It is what we use in here as addition is just normal vector addition. Anyway, so let's look at what he's doing here for how he's illustrating the vector addition as associative, right? So he is doing this via he's doing this graphically. So he has this same three vectors u, v, and w, right? So same three vectors u, v, and w here, right? And what he's going to do is he's going to add u to v first of all, get that result, and then add it to w. Okay, so he adds u to v first, right? And then he will add w to that, right? And then this light blue purple line over here is the answer, right? Okay, now what he's going to do is he's going to do this, right? He's going to add the v to the w first, right? And then add the u to this, right? Notice he's preserving the order, right? It's not to say that he's shifting the u to this point, right? The u has to come first, right? Okay, so you add the v to the w first to get this brownish line here, right? And then you add the u to that and you get this result. And notice it's the same answer, right? You see that this vector here is the same as this vector here. Right, okay, and there exists a zero vector in your vector space such that any vector plus that zero vector is just gives you the same vector, right? Okay, and if you're in R2, right, if you're looking at the plane, right, then the zero vector is just naturally what you think it would be, 0, 0 over here, right? Okay, and right, so your vector 2, 3, right, is going from here to here, right? This, you're going 2 horizontally and 3 vertically, right? But your vector 0, 0, you're not going anywhere, right? And because you're not going anywhere, your start point and the end point are the same, right? So really you could just conceptualize your zero vector as just being a dot, right? Okay, and what he's showing here is that when you add the zero vector, right, to a vector, right, nothing happens, right? You just keep the same vector, right? So, oh, well, more precisely, what he is justifying is, I guess, he's or showing an example of, is that if you take this zero vector, right, and you add it to this 2, 3, right, you still keep the original vector. Right, and now what he's looking at is he's gonna consider additive inverse, right? Alright, so this is his given vector v over here, right? And what he wants to do is he wants to get an inverse of it, right? Okay, so the inverse, so this is v over here. What he wants to get is a vector w that when you add this to the original v, you're just going to get the zero vector, right? And I think we all know what it's going to be. It's going to be, the inverse is going to be minus 6, minus 2, right? But he's illustrating it graphically. Okay, so it's going to modify this 2, 3 over here, right, to get something that is the inverse. Right, so he drags it along, and notice he's using minus 6, minus 2, right? And the point is that the v is the green, right, going from here to here. So you go from here to here. And with the inverse, you just go backward, right? And then you just end up with 0, 0, right, which is the zero vector. Okay, and he's pointing out that this is the original vector 6, 2, right? How you get the inverse is, at least in the case of R2, you could just take the negative of 6 and take the negative of 2, right? Right, okay, so now he's talking about commutative, right? So what is commutative, right? Right, so it's something like this one over here, right? But not quite the same thing. This one was with three vectors. This is just two, right? And notice over here you kept the order, right? This is u, v, and w, and you actually sort of kept the order u, v, and w, right? You didn't mix this around. You didn't bring the u over here, right? But commutative, what commutative means is that you can change the order, right? So u plus v is equal to v plus u, right? And normal addition of, say, like integers is commutative, right? So if you have 1 plus 2, 1 plus 2 is equal to 2 plus 1, right? Right. A next example of, well, an example of something that is not commutative is you can use the cross product again, right? Because I cross j, for example, is k, right? But j cross I is minus k, right? Okay, so uh, cross product is not commutative, but this normal vector addition, right, where you just add the components, it is commutative, right? And he's illustrating this in this diagram. Okay, so add the u to v, and notice the u is first and then the v is second, and you're going to get the 2 minus 7. Okay, and here what he does is he uses the v first, right? So you start with the v, then you add the u, right? And you get the same answer, right? The 2 minus 7. Okay, and he's trying to illustrate the closure under scalar multiplication, or the scalar closure, right? So this is a vector in the plane, right? And if you multiply it by a scalar, the vector will remain in the plane, right? It will actually stay in the same diagram, right? But the main thing is that it actually remains in the plane. Okay, so he's multiplying by different scalars, and he's showing you that well, the length is changing, but it still just remains in the plane, right? So if you have a vector v to start off with, and then you multiply it by scalar, right? Okay, so notice the condition is that the vector v, green v, is to start off with in the vector space, and you multiplying it by a scalar, right? And the scalar multiplication over here results in something that remains in the vector space. Okay, so there's 4 more properties that we need to look at. So in the order that he is doing it in his video, it's distributive over scalar addition, right? So that's this one over here. Then distributivity over vector addition, which is this one over here, right? And then the scalar multiplication associativity, which is number 9 over here, and then the last one, the 10, coincides with mine, right? Okay, so the 2 distributive properties, then this scalar associativity, and then the identity, right? So let's take a look at what he does. Okay, so this is the distribution over scalar addition here, right? So the idea here is that adding 2 scalars. Okay, so this deals with scalar multiplication, right? I have 2 scalars here. I added first the scalars first of all. So the scalars are r and s, right? I add the scalars and then I multiply by the vector v, right? Alternatively, what you can do is you can the 2 scalars over here, right? Okay, so it's as if you're multiplying throughout, right? So if this were just say like normal, say like integers and so, right? What you do is it would distribute, right? It'll be r times v and then s times v, and then you add, right? Okay, and in the context of vector spaces, it's actually this same idea, right? Okay, so you have your two scalars over here inside, and you can add them first of all, multiply by v, right? Or the scalar r you can multiply by v, and then the s you multiply by v, and then you add both of those. And if you do it this way, or you do it this way, you get the same answer, right? And that's what he's illustrating by this diagram, right? So the vector v that he's using here is vector 3, 2, right? And he wants to demonstrate the scalar addition distributing over your vector here, right? Okay, so the vector v is 3, 2, right? Now the scalars that he is using is 2 and 3.75, right? So the r is 2 and the s is 3.75, right? Okay, so here what he does is he adds the r to the s, right? So the 2 plus the 3.75, which is 5.75, right? And then the 5.75 multiplied, say, against the 3 would give you the 17.25. And similarly, the 5.75 against the 2 gives you 11.5, right? So this left-sided equation is graphically represented by this arrow here, right? So this is the vector 3, 2. You multiply by 5.75 and you get this one over here, right? For the right hand side, what he's doing is he's taking the same vector v and multiplying by r first of all, which is the 2, right? So when you multiply this over here by 2, you get 6, 4, right? Okay, and 6, 4 is from here to here, right? Notice there's an arrowhead over here, right? Okay, so you're going from here to here, so this is RV, right? So RV is from here to here, right? And then he multiplies s times v, and the s is 3.75, right? So the 3.75 times the 3.2 gives you this over here, right? So 3.75 times the vector gives you this, right? So this is 2 times this vector, and then 3.75 times this vector. So you get this one is from here to here. This one is from here to here, right? And what he's illustrating is that if you add these two vectors, you get the same as this left-hand side, right? Which is this one here, right? All right, okay. And the next one is distribution over the vector addition, right? Okay, so right. So again, you have an equality over here, right? So in say simple terms, if this was integers, right, you'd have r times v plus w, and you'd expect to be able to multiply r times v individually and then r times w and then add, and you'd have equality over here, right? Okay, and that also goes for your vector spaces, right? So he has an example here, right? Right, so v is vector 6, 2, w is vector 3 minus 5, right? Right, okay, and this left hand side is first you add, okay, so you have, sorry, the v, right, which is the 6, 2. You have the w, which is 3 minus 5, and then the scalar r is what he's using as scalar r is 1.75, right? Okay, so right, okay, so we look at the left hand side here first, right? Your left hand side here first is you add the v to the w first of all, and you get this pink arrow here, right, which is 9 minus 3, right? And then so v plus the w gives you this pink arrow, and then you multiply by 1.75 to give you this longer pink arrow here, right? Right, okay, on the other hand, what you could do is you could just multiply the v first by the 1.75, and that gives you from here, right, to here, right? Okay, so you go from here to here, and that's the v 1.75. And then the 1.75 times the w, right? So this w over here, you're going to multiply by 1.75, and that is this dashed blue line here, right? Okay, and when you add the r times v plus the r times w, right, you're going to get, so this is the rv plus the rw, gives you this the sum of the RV plus the RW gives you this long pink line, right? And the pointer is this vector here, right? This long pink line is what this is equal to, and that actually is equal to what you got by adding the V and the W first and then multiplying by R, right? Which is this. Okay, so the length of this vector is equal to the length of this vector. And so this is simply a graphical example, right? It is not a proof, right? Okay, so this one is the scalar multiplication associativity, right? Okay, so again, you can think of this to get an idea what the associativity is for the multiplication, right? If you have, say, three integers over here, right? If it was three integers, what you'd have is, for example, if you had, say, 2, 4, 2, 3, and 4, right? So if we had 2, 3, and 4, right, what we'd have is 2 times 3, which is 6, right, times the 4, which would give you 24, right? Or if you have the same 2, 3, 4, right, what this is saying is you multiply the 3 times the 4 first, right, which would give you the 12, and then 2 times the 12 would give you 24, right? Okay, so if you do in, say, like just normal multiplication, it doesn't make a difference which ones you group first, right? You could group the R and S first, or you can group the S and the V first, right? Okay, but this is different. We're talking about vector spaces over here, so they're actually different. These two are scalars, while this one is a vector, right? But it's a similar sort of idea, right? So what this is saying here is that if you want to work this out, right, you can multiply the R and S over here, and this is bad notation because this should just be normal multiplication of R and S, right? This is not a dot product. This is not a scalar multiplication, right? This is just multiplication in a normal sense, right, of real numbers. Okay, so this dot shouldn't be there, right? Anyway, so you have R times S first of all, right, and then multiply by V, right? Or you can take the scalar multiplication. You can form the scalar multiplication of S and V, right? Work out what this vector is, and then take the scalar multiple of R times this vector here, right? Okay, and he has an example of this, right? So your vector V is 4, 2, right? So he has this as his example vector, right? And the scalars that he's using for R and S would be 2.75 and 1.5, right? I've frozen the video at this time, right? But you can actually adjust what the S and the R are by using these buttons here, right, in the video. Anyway, sorry, not in the video, but this is part of a GeoGebra app, right? So he's doing a screencast where he's showing his GeoGebra app. Okay, right. Okay, but you can use what he's using over here at this point in time is that the R is 1.5, right, and the S is 2.75, right? So R is 1.5, S is 2.75. Right, okay, so, well, how do you work this out, right? What you could do is you could multiply the R and the S first of all, which is what's happening over there, and then multiply by the V, right? And you get this, okay, so this is the V to start off with, and then you have the scalar times the V, which means that you get a vector parallel to V, but of a longer length, seeing that the scalar over here is bigger than 1. Right, so that this over here is the left hand side of this equation, right? Right, alternatively, what you could do is this V over here, you can multiply it by the 2.75 first, right? And that gives you this red arrow here, right? Okay, and then you multiply this vector by 1.5, right? Which means that this red arrow is going to enlarge further, right? And the total vector that you would get, right, would be starting at this blue dot and ending at this tail over here, right? And what you want to notice is that the answer here is the same as the answer here, right? So this is what he's trying to illustrate, right? He's illustrating this vector equality here, right? All right, so your last one here is identity element of scalar multiplication, right? Okay, so well, identity element, there should exist some element, some scalar, such that when you multiply it against the vector v, right, you just get the original vector, right? So that would be an identity element, right? And in case of, say, standard vector spaces, right, where you're using standard vector addition and standard scalar multiplication, your identity element is just going to be 1, right? The normal 1 for reals, right? Okay, and he says a simple example over here because there isn't that much that you can show, right? Okay, so this is an example of a vector that he has, right? And then you take take that vector and you multiply it against the scalar 1, right? So using scalar multiplication. Now the scalar multiplication of a vector in two-dimensional space, which is R2, right, means that you take in the scalar 1 and multiply it against each of the components, 1 times 5 and then 1 times 2, right? 1 times 5 is just a 5 and 1 times 2 is just a 2, right? So nothing happens over here and you just keep the same vector, right? Alright, so I stated previously that your set of vectors in the plane, right, set of all vectors in the plane, which is this over here, right, with your usual vector addition and the usual scalar multiplication is a vector space, right? I stated that, but I didn't prove it, right? So what I want to do is we want to talk about how you'd prove that now, right? Okay, now this is for R2, right? R2 is when you have vectors with two components in it, right? You can generalize R2 to Rn, right? So this over here, R2 is a particular case of Rn. Okay, so this R2 over here is a particular case of Rn when the n is equal to 2, right? So if the n is equal to 2 over here, the notation is that this n over here would be 2, right? So you wouldn't have these terms, right? Now, the point about doing this over here is that you could consider, say, more other cases as well, right? So if you had R3, right? R3 would mean U1, U2, and U3, right? And say R5 would mean U1, U2, U3, U4, and U5, right? Okay, so Rn over here means that it's just you consider vectors now with n components, right? Small n components as compared to say R2 when you consider n vectors with just two components over here, right? Right, and you want to notice, well, how do you do the vector addition, right? How you did the vector addition over here for R2 is you just add corresponding components, right? You add the x1 to the x2 and you add the y1 to the y2. Right, so likewise over here, right, I'm using just slightly different notation, but how you do the addition of vector u to vector v is you just add the corresponding components, right? So you add u1 to v1, and you add the u2 to v2, and so on, right? And you add the un to vn, right? So it's the same thing you're doing over here, right? You just add in the corresponding components. And the scalar multiplication here, how did you do it? You just multiplied each component by the scalar, right? And notice you're doing the same thing here, right? You're just multiplying each component over here by the scalar c, okay? Right, so this here is a generalization of the R2, right? Which means that if you can prove for this over here, right, we can prove, well then that would, if you can prove that Rn is a vector space, well then that would prove that R2, R3, all of them would be vector space. So in a way it's sort of like proving something by induction, right? Proving it for all n, where n is equal to 2, 3, 4, so on, right? but it's not going to be a proof by induction, right? You don't have any kind of induction step over here. Really, you just, all you're doing over here is the proof for this would be similar to the proof if you're doing it for R2. You just need to keep track of the notation a little bit. All right. So I want to show that Rn, right, which consists of vectors with n components, with the usual vector addition and the usual scalar multiplication is a vector space over R, right? Now, if you're going to show that it's a vector space, you need to prove all 10 of these, right? If I mean, on an exam, I wouldn't expect you to, I wouldn't ask you to prove all 10, but I'd expect you to prove any of them, right? So what I'm going to do here is I'm going to prove 4 of these, right? And the 4 that I'm going to prove is 1, 3, 4, and 7, right? So 1, 3, 4, and 7, okay? Right, okay, so let's start with 1, right? So we need to show additive closure, right? So additive closure is if I have 2 vectors belonging to my vector space, right? Then the sum of them is also belonging to the vector space. Okay, so you have u and v, right? So basically you're choosing any u and v in Rn, right? So, and you consider the sum u plus v, right? Alright, at some point in time you'll need to write out the components, so we do it over here. So the vector u in component form is this over here, and the vector v when you write out the components is this, right? And then you add them, right? Now adding means that you add corresponding components, so you get u1 plus v1, u2 plus v2, and so on over here, right? Alright, so this is what I have as u plus v, and I just need to justify that this belongs to Rn, right? But what is Rn, right? Rn is really just all vectors where each entry is a real number, right? And if you look at this over here, right, because u1 is real and v1 is real, when you add 2 real numbers, you're going to get an x real number, right? It's not to say that you're going to get a complex number or anything like that. Sum of 2 reals is just a real, right? And likewise, this is also a real number. u2 plus v2 is a real number, and so on for this one up to this one over here, right? So each of the components here is a real number, and that means that because each of these is real, right? By definition, this vector belongs to Rn, right? Because Rn consists of the set of all vectors, all possible vectors with real components here, right? Okay, so that's how you would justify the first one, how you'd prove the first one. Okay, so let's look at proving this third one over here, right? Additive identity, right? There's some vector, right, called a zero vector, right, such that if I take any arbitrary u belonging to my vector space, right, so if I take any u belonging to my vector space, which is Rn, and I add this zero vector to it, right, I'm just supposed to get back u, right? Okay, so u plus 0, adding 0 doesn't do anything, and I get back my original vector. Right, so this here is there exists a zero vector. This is probably a little tricky because you need to actually know what this zero vector is, right? In the case of when you just have standard usual vector addition and usual scalar multiplication, then the zero vector is what you expect it to be, right? If you had, say, like some sort of non-standard vector addition and non-standard scalar multiplication, right, then your zero vector may not be just your standard zero vector like this here, right? It may be something else, but in this case we don't need to worry about it, right? So part of this proving this is you actually need to know what this zero vector is, and in this case the zero vector is just when all your components are just a zero real number, right? And once you identify that zero vector, you just need to justify that when you take any arbitrary vector in your vector space Rn, right? And you add 0 to it, you're just gonna get back the same vector, right? And this isn't hard to show, but you do need to just write it out, right? Okay, so the vector u, and all of these, eventually you need to probably write out your components, right? So the u over here is u1, u2 up to un, right? So the components are there. The 0 vector just has 0 in each of the components, and when you add, right? And now you add. When you add, you just add corresponding components. And here I have u1 plus 0, and these are just u1, which is a real number, added to 0, just normal 0, 0 in the reals, right? And when you add any number to 0, you just get back the same number, right? So likewise, you get u2 plus 0 just gives you u2, right? And this over here is simply just your original vector, so this is u, right? So what you just did is you just proved that u plus your 0 vector, u plus the 0 vector is equal to u. Right, okay, or well, more precisely, what you showed is for this 0 over here, which consists, this 0 vector, which consists of all your components 0 over here, that has this property, right, that u plus 0 is equal to u. Right, okay, so fourth one that I want to prove is the additive inverse, right? So if I have any vector in my vector space, I can always get a vector that is minus u, right? This means the inverse or the additive inverse, right? Okay, so if there's for any vector u in my vector space, there exists additive inverse such that u plus my additive inverse just gives me the 0 vector. Okay. Right. Okay. So you want to notice that so u plus the additive inverse will just give me the 0 vector, right? But in order for you to do this, right, you need to know what the 0 vector is in the first place, right? Okay, and the only way that you know what the 0 vector is if you identified what it is from part 3, right? Okay, or you just know what it is for your particular vector space, right? Anyway, so let's prove it for this case of Rn, right? So for any u, right, in my Rn, right, which is how you write it like this, right? Okay, what you need to do is you need to come up with the additive inverse, right? Okay, so what would you use as the additive inverse, right? What you would do is you take the u1 and take the negative of that. You take the u2 and take the negative of that, and take un, you take the negative of this, right? In other words, you take in this vector and you multiplying it by the scalar minus 1 to get this, right? Okay, and this here actually, it is an Rn. You want to make sure that this vector, this additive inverse of this one over here is in fact also an Rn, and that's true because each of these are just real numbers, right? Anyway, so this over here is your candidate additive inverse that belongs to Rn, and the final thing is that you want to justify that u plus this additive inverse would just give me the 0 vector, right? And that isn't hard, right? So you have u plus this candidate inverse here, right? Okay, and the u is u1 to un, so standard notation for the u written in component form. You have your additive inverse in component form, and now you add, right? And what you have is u1 plus minus u1, which would just give me 0 here. u2 plus minus u2 would give me 0, and each of these components would be 0, so this is the 0 vector, right? Right, and once you establish that you have your you found an additive inverse such that u plus the additive inverse is the 0 vector, right? That justifies that this candidate additive inverse is in fact an additive inverse, right? I mean, you can cook it up, right? But you still need to test it, right? So the u plus this over here turns out to be 0, so that means that this here is your additive inverse, right? What this shows is for any vector in Rn, remember this is an arbitrary choice of a vector in Rn, you could always find a corresponding additive inverse. Okay. All right. Okay. Last one here is that we want to show is a scalar multiplication associativity, right? Okay, so we want to show this equality over here, right? C1 and C2 are any scalars, and U is a vector, right? Right. Okay, so with these say these three over here, usually is just best if you just start with one side and you work your way to the next side, right? Okay, so I have uh, this expression here, which is this left hand side, and I want to show that the left hand side is equal to this right hand side. Right, so what is this, right? You have your vector u and you're multiplying by scalar c2 first, right? You working this out, and then the resultant vector that you get is you multiply that against c1, right? So that is what you're doing over here, right? So let's do it. The vector u is this u1 to un over here. Notice the brackets, right? So the brackets over here means that you're going to multiply by c2 first. So this is a normal scalar multiplication of this vector by c2, right? Okay, and now what you have is a c1 outside over here, right? Okay, so it's going to be c1 times this component over here, right? Now you want to be careful about how you're using your brackets over here, right? When you go from this line to this line, from first line to second line, right? When you're looking at the right hand side, what you did is you multiply the c2 times u1, right? So this actually exists as a product already, right? So now when you're multiplying c1 against it here, right? You multiplied c2 by u1 already, right? So you multiplied c2 by u1 already, right? And this notation means exactly that, right? So it means that you multiplied c2 by u1 already, and now you're multiplying c1 by it, right? Okay. And likewise for your second component over here and up to end component, right? Alright, so I get this, but notice what I want, right? What I want is I want the C1 and C2 grouped together, right? Which means that I want to multiply the C1 and C2 first and then multiply against the vector, right? Okay, so I'd want to multiply the C1 and C2 first, but I can do that, right? Okay, so again, this is a product of three things where you multiply the C2 and the U1 first. But these are just real numbers here, right? So associativity or multiplication holds for real numbers. In other words, I can group the C1 and C2 first and I'd still get the same answer. So that's what I going from here to here. I'm just illustrating or writing down that I can this is equal to this where I group this C1 and C2 first. Notice also here on your second component I group the C1 and C2 first, and likewise over here. And now that I have this here, right, well, what is this, right? You're sort of working backwards now towards getting this right hand side over here, right? Okay, so you want to notice that this expression is what you would get when you multiply this vector u1, u2 to un by c1, c2, right? So c1, c2 times the u1 would give you this. c1, c2 times the u2 would give you this, and so on, right? Okay, and what is this, right? This is c1, c2 times the vector u, right? So what you just showed is by appropriately multiplying out and just really grouping, changing the grouping of the product over here, is that you prove that if you have a vector you multiply by c2 first and then you multiply by c1, right? That's the same as multiplying the scalars c1 and c2 first and then multiplying by u. Alright, so next type of vector space that we want to look at is polynomials. Okay, so polynomials where it's of degree of, looking at a set of polynomials of degree of at most n over here, right? So n is some fixed integer that is bigger than or equal to 1, right? So for example, I mentioned this in the beginning of this lecture, that P1 over here is polynomials, set of polynomials of degree at most 1, right? Okay, and this here would be a generalization of that, right? So this would be polynomials of degree at most n, right? So for example, if I had P2, right, I would have A0, A1x, and A2x squared, and nothing else, right? Okay, so you if you have, for example, here polynomials of degree at most 1, in order for it to be a vector space, you'd need to know what the vector addition is and what the scalar multiplication is. And the vector addition in this case, right? So what you're doing is regarding the polynomials themselves as being vectors, and what you gonna define as vector addition is just a normal addition of polynomials, right? So for example, this here is one element from this set, 2 plus 3t. This here is a next element, 1 minus 2t. And then to add these, the vector addition over here is just normal polynomial addition, which is 2 plus 1, 3 over here, and 3 plus minus 2, which is 1 here, right? So I get 3 plus t, right? And then the scalar multiplication is just the standard way that you multiply a polynomial against a scalar, right? You just multiply each coefficient here by the scalar, right? So you get 2 times 1, which is 2, and then 2 times 3, which is 6. Okay, so in this general case, the definition of the vector addition is the same thing, right? If I have two polynomials over here, the vector addition is just defined by just adding the corresponding coefficients, right? So here the constant term is a0, here the constant term is b0, so you add those. Here the coefficient of the x to the power 1 is a1, coefficient of the x to the power 1 is b1 on this side, right? And then what you do is you add the coefficients, so you get a1 plus b1, right? Okay, so the addition for the vector addition is just normal addition of polynomials where you just add in the coefficient of like powers, right? So here the power is x to the 1, and here the power is x to the 1, and you add the corresponding coefficients. And the scalar multiplication is defined just as in the case of P1, you just multiply the coefficients over here each by the scalar, right? So a0 times okay, so if your polynomial is noted as a0, a1x up to anx, right? Then it's c times a0, c times a1x, and so on, right? Right, one last thing to note before I give a proof of one of these axioms is that for two polynomials to be equal, it means that, and for two polynomials in Pn, sorry, so two polynomials of degree less than or equal to n, right? In order for them to be equal, the corresponding coefficients must be equal, right? So for this polynomial P1 to be equal to P2, the A0 has to be equal to the B0, the A1 has to be equal to the B1, and up to the AN has to be equal to the BN. Alright, so this is polynomials of degree at most n over here, and the notation, the small n over here is to indicate the maximum possible degree, small n, right? Okay, so I'm not going to prove many of these. I will prove, I'll go through this, the second axiom over here, which is the associativity of the vector addition. And then you should take a look at the others here, right? And being able to do these, you'd be required to be able to prove these over here, the 10 axioms. Okay, so what we want to do is we want to show associativity of the vector addition. Alright, so I want to prove the associativity of the vector addition, so I want to prove this one over here, right? So number 2, right? Additive associativity. Alright, so it involves 3 vectors from your vector space, right? So my vector space over here is set of polynomials, so the 3 vectors here would be 3 polynomials, right? And notice how it's grouped, right? So you have 3 of them, on this left hand side you add in the last two, right? And then you add the first one, and on this right hand side you add the first two and then add the third one. Okay, right, so let's start over here, right? So these are all P1, P2, and P3 are all elements of Pn, right? So polynomials of degree at most n here, right? So I denote the P1 by A0, A1x, ANX, the P2 by B0, B1x up to BNX, and P3, C0, C1x up to CNX, right? Okay, I notice I have this bracket around here, which means that I'm going to add P2 and P3 first, right? So I'm adding P2 and P3 first, right? And when I add these, I add the corresponding coefficients, right? Okay, so the constant term over here is B0, C0. The coefficient of the x over here is B1, C1, right? And so on, right? Okay, so now that I have this polynomial over here and this one here, right? This polynomial. Then I add this first one to the second polynomial, which means that I'm adding coefficients from like terms, right? So the constant term is 0 here, I'll add to the B0 plus C0. You want to notice the grouping over here, right? The grouping over here means that you added the B0 to the C0 before, right? And now you're adding the A0, right? And likewise, you add the A1 x term to the B1 plus C1 times x over here, right? And again, notice the grouping, right? You added the B1 to the C1 before, and then you added the A1, right? Right, and well, what are you heading towards, right? You're heading towards where you're heading towards this right hand side, right? So where you added the first two polynomials together and then you added the third one, right? So what you want to do is somehow you'd want to change the grouping over here, right? And to change the grouping you start right here, right? Okay, so notice that A0 plus B0 plus C0, right? Where I added the B0 and the C0 first. I can always write as A0 plus B0 in brackets plus C0, right? And I can do that because these are real numbers, right? And real numbers have this additive associative property, right? Okay, so likewise I can change the order of the brackets over here. And once I have this, what I start to do is I start to work backwards, right? I notice that if I add polynomial C0, C1x, Cnx to this polynomial over here, I would get this fifth line over here, right? Okay, and again, basically what you're doing is you're working backwards, right? So one way to do this, probably not the most elegant way to do it, right, is to start with this and then work your way forward. And you want to see if you get it to match in the middle here, right? Okay, so now that I have this polynomial here, right, first one, I can split that into the sum of these two, or I should realize that when I add these two, I get this one, right? Right, so once I come down to the second to last line, what I have is I have that I have it grouped, right? It's the first polynomial over here plus the second polynomial. I added that first, and then I added the last one, right? Which is what I want to get on this last line. Right. So the last type of vector space that we want to look at would be matrices. Okay. So my notation over here is big M for matrices, and the small m is I'm looking at matrices of a certain size, right? So small m is the number of rows, and small n is the number of columns here, right? Okay, so I'm looking at matrices of size m by n here, right? And the r over here means that I'm looking at matrices with real entries, right? So I'm not allowing, not in this class, we're not doing complex entries, right? Okay, so I'm considering the set of all matrices of size m by n, right, with real entries, and the vector addition that I'm going to define for this set of matrices is your normal addition of matrices. When you add two matrices of the same size, you add corresponding elements. So for example, on the 1, 1 element, you add A11 to B11, right? And then you add A12 to B12 and so on, right? And then you define the scalar multiplication of so a scalar times a matrix, right? Well, A is regarded as a vector inside it. The matrix A is regarded as a vector inside there. And the scalar multiplication is in fact a normal multiplication of a matrix by a scalar, which is you just multiply each of the entries in the matrix by the scalar outside over here, right? Okay, so this set of all matrices of size m by m, all real matrices of size m by n, right? With this vector addition and with this scalar multiplication, this will form a vector space. Okay, so you'll do the proof of that in tutorial, right? But really the idea is that it's similar. The proof for these over here, it's similar to the proof for the Rn, right? And the reason being is really you just really need to keep track of the entries. Whatever, notice over here, what you're doing is you add in corresponding entries in Rn. Notice over here, you just add in corresponding entries, right? So it's really just the same idea as in Rn. It's only that the elements are written in a single row like this over here. But here the elements are distributed around a matrix. Okay, so you'll see that in tutorial.